Okay, welcome back from the coffee break. I'm really happy to introduce Conrado to talk about affirmative sampling. I think we all wish he was here, but we're going to actually hear two talks from Conrado, and I'll introduce the next one in half an hour. So go ahead, Conrado.
Thank you very much, Bob. This is a joint work with Jérémie Lumbroso from Princeton and myself. Jérémie hasn't been able to attend. I think maybe he's made it, but I don't think so. Let me go directly straight to the problem. The scenario, the problem we want to solve is to draw random samples from a very long sequence of items from a data stream. Here I wrote Z equals Z1, Z2, Z3, etc. up to Zn, but more often than not, we will in the online scenario where we keep receiving elements as a fast pace, and we want to sample, get a random sample from the elements we've seen so far at any given moment, and then we get that sample, and then new elements keep coming. And the thing is that those elements are drawn from some large domain, and we would like to make some computations from this data stream, but we have several restrictions. First, we cannot do more than one pass over the sequence. We cannot offer the time to go many times through the sequence. We cannot spend a lot of time on each item that we see. We are typically seeing those elements at a very fast rate, and we cannot spend a lot of time on any of them. And that's the most important restriction, probably. We have very small additional memory. We cannot keep the data stream in memory. We only have maybe a constant number of bytes to store information, or maybe in the log n, which is not that big. Even for very large n, log n is not that large. But we cannot store the data stream, and we cannot store large portions of the data stream. So we don't have linear space. Moreover, we won't like to have any hypothesis on the data. We cannot suppose that those Zi are drawn from some specific source. And there are many different applications for this model. In particular, applications in network traffic analysis, in database query optimization, information retrieval, data mining, etc. Many others. And there are problems like the one of sampling, which is the one we will focus in. But there are many others, very famous problems. And before I formalize those problems a bit, we often see the data stream as a multiset. So we have actually small n distinct elements, and each one of these distinct elements occurs a number fi of times. So the sum of the fi's is capital N. And the small n is called the cardinality of the data stream, the number of distinct elements. And so the first problem, our very famous problem, and actually one that Philippe Flageolet made very popular, and he discovered together with other people many of the most successful and well-known algorithms for the task, like log-log and hyperlog-log, is finding the cardinality of the data stream. This problem of finding the cardinality of the data stream is trivial if you had enough memory. But since you don't, it becomes a challenge. Another very famous problem is finding the top k most frequent elements, or also another, this problem appears in another flavor, finding the heavy hitters. They are also known as sea icebergs. Those elements whose relative frequency is larger than some threshold C. And now the problem we are interested in is drawing a random sample of distinct elements. Here I might stress that we are interested in distinct elements, because we can also be interested in finding drawing random samples of items from the data stream. So particular, every Zi is a different instance. So you might sample the same element many times because it's very frequent in the data stream. So now the point is how to sample to begin with, because you don't know the n, the small n. You don't know the small n cardinality. So how do you draw with probability 1 over n? And now there's an easy solution, which is folklore, so to say. Is known in some works in the literature as bottom k sampling, which is basically hashing every element in the data stream and keeping the elements with the smallest hash values. Here I've rewritten the algorithm in terms of largest hash values. So you keep the set of the k elements with largest hash value. You compare the hash of an incoming element with the minimum hash value you keep up to this point, and if it's smaller, you discard. If it's in the sample, if the element is in the sample, you have a repetition, and you don't want to have other than distinct element, k distinct element. And finally, if your element is not in the sample, but the hash value is larger than the minimum hash value that you keep in this table of k elements, you just make a replacement, right? So at any moment, you keep in this table, after you enter this this main loop, you keep the elements with largest hash values, and provided that you make a few assumptions, pragmatic assumptions about their hash function, this sample will be random, because basically any element gets a hash value, and this is essentially behaves like a uniform random number. Okay. So this is set again here. And in case that we used random numbers assigned to every distinct instance instead of the hash value, using the hash value is very useful to avoid repetitions, because the same element appears twice, it will have the same hash value. So this is what Philip called reproducible randomness. But if you use uniform numbers, random numbers, and you don't check for repetitions, like, oh, this element was already in the sample, what you have is a very famous algorithm that's reservoir sampling by Jeffrey Bitter. Another famous algorithm for distinct sampling is it's also known as distinct sampling in some works, but the initial name was adaptive sampling, was devised by Beckman in '84 and deep analyzed in depth by Flageolet in the early 90s. And this algorithm will produce a sample of up to B distinct elements. So the size of the sample will depend on n, but it's bounded by the constant B. The algorithm produces such a random sample with up to B elements. Typically, the expected size of the sample will be between B halves and B with high probability. And at the same time, it produces a good cardinality estimation of the size. Of the cardinality. That's a mistake. It's not as cardinality estimation of the size of the. It's a. You have cardinality estimation using the size of the sample, final size of the sample. Now, what we wanted is, what if we want a sample where the size of the sample depends and grows with n? Because the idea is, if you have a data stream with a large cardinality, you want larger samples. You want that your sample is more representative of the fact that there's a large cardinality. It's more representative. You have a bit more representatives of the different types of elements that occur. At the same time, we want this to be a random samples, and that every element that you sample has the same opportunity of being sampled. And because of this combination of two properties, we call this affirmative sampling. And let me show you the algorithm in work. You start the initial phase, you fix K. And initially, you start with an empty sample. You see the first elements. I'm using here the hash values, and identifying hash values and elements is a small license. First element, you put it in the sample. Next element, you put it in the sample. Now you have two distinct elements. Now the third comes, and because it's larger than someone in the sample of two elements, you put it in the sample. But the other one, you keep. In the previous algorithm for distinct sampling with fixed size samples, you would have kicked out the 0.12, but you keep this. And now the size of your sample is 3. Next come a repetition. Now you discard it because it's the same element, okay? Something that you already had. Now imagine some other element comes, 47. It's larger than the second largest element in the sample. So you add it, it's among the k largest elements, and you keep those two. So your sample grows to size 4. It's not that you will put everything, right? Like for instance, this element 0.06 comes, its hash value is too small, it's discarded. It does not enter the sample. And now what happens if you I'm sorry, this one is another example of an element that has a very large hash value among the k largest values seen so far. So you keep in this part of the sample, and the rest you will keep in this part. So you'll have now that the sample is size 5. And actually, if you look at this sample, it contains the 5 elements with largest hash values seen so far. Okay, so those that you have here are the elements with the 5 largest hash values, and your sample keeps them. So it's a random sample. Among all samples of 5 elements that you can draw from this stream, it will be random. Okay. So, and here comes the most interesting part. What happens if you have one element like this that is not in this part, is not among the largest, the 2 largest elements, but still larger than some element in the sample, like it is larger than the sorry, this 0, this should be like this. So the 0.12 gets out, and this one replaces 0.12. And then imagine that this other element comes, sorry, and then this element that was in the sample is kicked out. So this is the summary of what we are doing. If we are keeping a sample of some size, we can think of the sample of two parts. The k elements here, this is fixed, and it will contain the elements with k largest hash values. And this is the variable part. And then what happens when a new element comes, z, with hash value z? If the z is larger than the smallest element here, this element is added here, and this element moves from the fixed part to this variable part. And the total size of the sample grows by 1. If the element that you see has a very small hash value below this z star, or is really repeated, you either discard it, this element is discarded, is not sampled, or what you do is you update information that you already kept for z in the sample. And last but not least, if the element, the new element, is between this element, the hash value of this element, and the hash value of this element, what you do is a replacement. You add this element, and this one is kicked out. So the total size of the sample remains the same, but you are sure that you will be keeping the s largest hash values seen so far. And therefore, it's a random sample of s elements. And moreover, that's the algorithm. Once you transcribe in pseudocode, not very difficult. Actually, it's only you adding this line compared. Oh, sorry, you are adding those lines. When the element has to be added, you add it, but you don't discard anyone. And when it's somewhere in the middle, in the kth largest and the smallest in the sample, you do the replacement. Okay, so those are the two lines that are different, significantly different from the other algorithm, but extremely simple. The point is that the size of the sample coincides with the number of k records in a random permutation of size n. So the sample is not containing the set of k records, but the s elements that you have are those that has large hash values in so far. Therefore, the sample is a random sample. Another important property is that when you add one element to the sample, it occurs the very first time you see that element, and it will be there in the sample ever since. So every time you see a new repetition of that element, you can update and keep exact counts of exact statistics about that element. Now imagine that at some point that element gets kicked out. It's thrown away from the sample. Well, you are sure it will never come back. It will never be put again back into the sample. And we call this property dependability. And there are many algorithms that are dependable, but there are other algorithms like reservoir sampling and other sampling algorithms that are not dependable. Now, the properties of the size of the sample are very well understood. We know that the expected value is k log of m divided k. blah, and the bias and the exact distribution and the asymptotic distribution of S. The value S, the size of the sample, can be used to estimate the cardinality. It's a cardinality estimator called recordinality, but that we introduced in 10 years ago. And if you do this computation, you plug the size of your sample after running the algorithm, the expected value of this is exactly n. It's an unbiased estimator for the cardinality. Essentially, you don't need to keep the full sample if you are only interested in cardinality estimation. You just need to keep a counter how many times you would have made grow the sample, and you only need to keep the k largest hash values. But our interest here is sampling, so we want to keep on everything. We want to keep the log n elements. We can also we understand also quite well how many times this replacement mechanism is used. In particular, expected number is k times the log square of n divided k. And from this information that we have about the size of the sample, the number of replacements, and a few easy probabilistic bounds, you can derive the expected cost of the algorithm, which is n. You have to process every element, and then basically you are paying for the log of the size of the sample, expected size, times the number of times you are doing those updates in the sample. So basically, you have this term, which is quite small compared to n typically. Now, once you have this sample, random sample, you can do things like, okay, how many distinct elements have relative frequency below some value? This is detecting so-called mice. Because you can keep counts on the frequencies, real frequencies, the exact frequencies of the elements in the sample, you just will count the proportion of elements that satisfy the property in the sample, and this proportion of elements that satisfy a property in the sample gives you is an estimator, an unbiased estimator of the proportion of elements that satisfy the property in the data stream. Or things like, how many elements do we have we seen during the last 10 minutes? We just need to keep timestamps in the data, in the sample. In general, the fact that we have a large sample will mean that we can make more accurate inferences. And if we denote by NP the number of distinct elements that satisfy some property, then this ratio between the number of elements that satisfy the property in the sample and the size of the sample will is an unbiased estimator of the proportion in the data stream. So basically, this is a folklore result, except that people often think, or I've seen all the time, that S is fixed, not with a random sample sizes. And this is valid for any algorithm that produces random samples of variable size, for any distribution of the S. In particular, it works for affirmative sampling, but we could do with other algorithms. Another interesting result is the variance. And here's the most interesting thing. This variance will depend, is proportional to the expected value of 1 over S, which is, of course, not equal to 1 divided E of S in general, but in the if you do the math for affirmative sampling, they are of the same order. And this is This means that the variance is going to zero slowly, but it's going to zero as n grows. Okay, so basically what we have is a result that the standard error is decreasing as this, and this is a very typical result in cardinality estimation and sampling in data streams. Is the error, the standard error of estimations is decreasing as 1 divided by the square root of the size of the memory. And remember this, the expected size of the sample will be log n divided. Okay. Now you can also do inferences about proportions. Not all so you can do inferences not only about proportions but also about the absolute number of elements that have some property. In particular, using those estimators. One is based on recordinality. You have C1, which is recordinality, and you know the expected value is n. So if you multiply this number by this ratio, you can prove that the expectation is NP, the number of elements that satisfy a property. If you use this one, which is inspired by the famous K minimum value in for cardinality estimation, is the size of the sample minus 1 divided by 1 minus the hash value of the smallest hash value in the sample. This is also an unbiased estimator of the cardinality n. And if you multiply this C2 by this ratio, you will get an estimation of an unbiased estimation of NP. This one is very, using C2 is very, for estimating NP is very accurate. But you can do things like estimate similarity indices. You can use two samples, one coming from A, one coming from B, and then computing the, say, Jacquard index between the samples will give you an estimate of the Jacquard index of the two original sets. You can do good approximations for quantiles if an element whose relative rank is close to the median, for instance. You can detect better some outliers because your samples, any element, despite the frequency, their frequency will have the same probability of being in the sample. So that's important in algorithms that that draw random samples from the data stream. You will have many repetitions. I'm just to conclude, instead of using the kth largest hash value as the boundary to decide whether you add one element to the sample without replacement, is to add the element to the sample or not, you can use a different some different criteria. Like you say, okay, my element has a hash value which is the top alpha percent of the elements. It's in the above the median of the elements in the sample. It's above the 10% best or largest hash values in the sample. So then, instead of having samples of size logarithmic size, they will be of size n to the alpha. This is well understood. The size of the sample using this kind of rule has been very well studied by a lot of people. Some in this room, like Mike, Mark and Swante, and maybe Guy Luchar is also here. The point is that the variance is even smaller because it decreases as n to the minus alpha. Okay. So, well, to conclude, we would like to extend this work so that we were able to produce samples of a fixed target size, or at least on expectation, to make the variance of the size of the sample as small as possible, avoid having very large variances. And also extend the affirmative sampling to the so-called sliding window model, where you only want some random samples, not from the very beginning, but only random samples of the last elements you've seen in the, let's say, in the last hour. Okay. So thank you very much for your attention. I think there will be a little time for questions.
Okay, thank you. Just time for a quick question. We don't want to take time away from the next speaker, which is also Conrado.
Yeah.
Any questions?
So, what's it? Is there any question?
Anyone online with questions? Nope, looks like we're back on track, Conrado.
Okay, so then
Next
I move
slide.
to this one.